The quantum question, a new kind of power. What if I told you there's a machine that doesn't just think faster, but thinks differently? What if this machine could explore a whole universe of possibilities all at once? That's the promise of a quantum computer. It's a bold claim, and it's surrounded by a lot of hype. So let's cut through the noise. Let's ask a simple question and chase down the answer together. How powerful is a quantum computer, really? We're going on a journey, and I promise to keep it simple. We'll use everyday analogies, things you can picture in your mind to make sense of this new frontier. No advanced math required, just your curiosity. This isn't about replacing the laptop on your desk or the phone in your pocket. This is about a new kind of tool for a new kind of problem. Think of it like this. For centuries, we looked at the stars with our eyes. Then Galileo came along with a telescope. He didn't just see more stars, he saw moons orbiting Jupiter. He saw the phases of Venus. A quantum computer is like that telescope. It's a new instrument that lets us perceive reality at its most fundamental level and use those rules to solve some of humanity's biggest challenges. We're going to explore what these machines are, how they work their magic, and where that magic falls short. So, let's begin. The cosmos, even the one inside the atom, awaits. Bits and qubits. The language of computers. To understand a quantum computer, you first have to appreciate the computer you're using right now. Every device you own, from your smartwatch to your smart TV, speaks a simple language. It's a language of bits. A bit is the most basic piece of information possible. Think of it as a light switch. It can either be off or it can be on. There's no in between. We label these two states with numbers, 0 for off and 1 for on. Every email you send, every photo you take, every song you stream is ultimately just a fantastically long sequence of these ones and zeros, these simple on or off switches. Your computer's processor is a master of flipping these switches at blinding speed. It can flip billions of them every second. This incredible speed is what allows it to perform all the tasks we take for granted. But here's the key. It's a sequential process. It's tackling one thing at a time, just very, very quickly. To solve a complex problem, like finding the best route for a delivery truck with 1,000 stops, it has to check one route, then another, then another. Even with all its speed, some problems have so many possible routes that even the fastest supercomputer on Earth would need longer than the age of the universe to check them all. Now let's step into the quantum realm. A quantum computer doesn't use bits, it uses quantum bits or qubits. A qubit is a different kind of switch entirely. Instead of just being on or off, a qubit can be in a combination of both states at the same time. The quantum weirdness, superposition, and entanglement. We've touched on superposition, that idea of a qubit being both 0 and 1 at the same time, like a spinning coin. This is the first pillar of quantum power. It allows a quantum computer to consider a vast number of possibilities in a single computational step. Instead of a single soldier marching down one path, you have a whole ghost-like army exploring every possible path through a maze simultaneously. This parallel exploration is what gives quantum computing its potential for a massive speed-up on certain problems. It's a new way to navigate the immense landscape of data. But there's another layer of weirdness, even more profound. It's a phenomenon Albert Einstein famously called spooky action at a distance. We call it entanglement. Imagine you have two of our special quantum coins. You entangle them, linking their fates with an invisible cosmic thread. You give one to a friend, send them to the other side of the galaxy. You stop your coin. It lands heads. Instantly, you know your friend's coin is heads. There's no signal, no communication across space. Their states are perfectly correlated, no matter the distance. This spooky connection is a crucial resource for quantum computation. It's like a team where everyone knows what the others are thinking without speaking. It's not just more computing. It's a new mode of existence for computation itself. Interference, the wave that finds the answer. We have our qubits in superposition, exploring many possibilities at once. We have them entangled, linked in a spooky, powerful harmony. But how does this get us to a single, useful answer? After all, when we measure the qubits, they just collapse into a random string of zeros and ones. This is where the third and final piece of the quantum puzzle comes in: interference. This is the secret sauce that makes a quantum computer a calculating machine, not just a quantum slot machine. It's how we steer that vast exploration toward the right answer and away from all the wrong ones. Think about waves in a pond. When two wave crests meet, they combine to make a bigger wave, constructive interference. When a crest meets a trough, they cancel each other out, leaving the water flat, destructive interference. In a quantum computer, every possible computational path acts like a wave. A quantum algorithm is a carefully choreographed sequence of operations designed to control how these waves interfere with each other. Set things up so wrong. Answer paths cancel out, right answer paths reinforce each other. The waves for the right answer get bigger and bigger. After running the algorithm, when you measure the qubits, the probability of the correct answer is dramatically amplified. Wrong answers weren't checked one by one, they've been canceled out by wave-like quantum mechanics. It's an elegant and powerful way to find a needle in a haystack. This is what separates a true quantum algorithm from a random process. Classical computers inspect every piece of hay. Quantum computers, through interference, make the haystack transparent, leaving the glowing needle. Quantum computers embody a different problem-solving philosophy written into the fabric of the cosmos itself. So, we have this powerful, strange machine. What is it actually good for? It's not a universal tool. For certain problems, its potential is revolutionary. These are combinatorial problems where possibilities explode beyond classical reach. Quick tour of quantum sweet spots. First up, chemistry and materials science. Simulating molecules is hard because electrons are quantum objects. Quantum computers can model them naturally. This could unlock new drugs, better batteries, catalysts for clean energy and carbon capture. Next, logistics and optimization. A delivery truck trying to find the shortest route to visit 100 cities. The traveling salesman problem. Classical computers face astronomical route counts. Quantum superposition and interference can explore many routes and find very good solutions faster. Could revolutionize supply chains, airline scheduling, complex financial modeling, saving billions and cutting energy use. The double-edged sword, cybersecurity. Most online security relies on the difficulty of factoring large numbers. Shor's algorithm could factor efficiently and break many codes. That's a threat, and also a catalyst. Scientists are building post-quantum cryptography to resist both classical and quantum attacks. Finally, quantum search. Imagine an unsorted database, a huge, messy phone book. Classically, you check about half the entries on average. Grover's algorithm finds the items significantly faster. Applications, genomics, applications, artificial intelligence, finding patterns in mountains of data. Section 6. The reality check. What quantum computers can't do now for a dose of cosmic perspective. With all this talk of incredible power, you might be wondering if a quantum computer will one day make your video games load faster, help you write an email. The short answer is no. It's crucial to understand that a quantum computer is a specialist, not a generalist. For the vast majority of daily tasks, browsing the web, editing a document, watching a video, a classical computer is, and will likely remain, far superior. These tasks are sequential and lack the mathematical structure quantum machines exploit. Think of it this way. A Formula One race car is engineered for incredible speed, but you wouldn't use it to go grocery shopping. It's terrible in traffic, has no trunk space, and is incredibly inefficient for short trips. A quantum computer is like that race car. It's designed for a very specific track. Problems in quantum simulation, optimization, factoring. For everyday computation, your family's sedan, the classical computer, is more practical, efficient, and reliable. A quantum computer struggles with simple arithmetic basic data movement that classical chips do effortlessly. Furthermore, a quantum computer doesn't just spit out a single perfect answer every time. The process of measurement, as we've discussed, is probabilistic. So you often must run the algorithm multiple times and take the most frequent result. A future of partnership. Classical and quantum each playing to their strengths. Section 7. The Great Hurdles. Why this is so hard. If quantum computers are so powerful, why don't we have large-scale, fault-tolerant ones already? The answer is that building and operating them is one of the greatest engineering challenges of our time. The very quantum properties that give them power, superposition, entanglement, are incredibly fragile. The universe is a very noisy place. The slightest vibration, a stray magnetic field, a tiny change in temperature can disturb the delicate quantum state of the qubits. This phenomenon is called decoherence, and it's the ultimate enemy of the quantum programmer. When decoherence occurs, the quantum computation is ruined. The superposition collapses, the entanglement is broken, the information stored in the qubits leaks out into the environment, becoming useless noise. To fight this, scientists must go to extraordinary lengths to isolate their quantum chips from the outside world. You often see quantum computers that look like giant, elaborate chandeliers inside a massive cylinder. Those are dilution refrigerators. They cool the quantum chip down to temperatures colder than deep space, a fraction of a degree above absolute zero. This extreme cold quiets thermal noise and keeps qubits stable for just a little longer. Even with shielding and cooling, errors are inevitable. A qubit might spontaneously flip from 1 to 0, or its phase might drift. To build a useful quantum computer, we need to correct these errors on the fly. This is quantum error correction. But current codes need huge overhead, hundreds or thousands of physical qubits per logical qubit. We may need millions of high-quality physical qubits to create a few thousand stable logical qubits. Section 8. Building the future. How do we measure progress? With all these challenges, how do we even know if we're making progress? It's not as simple as just counting qubits. A computer with a million noisy, error-prone qubits might be less powerful than a computer with just a few dozen very high-quality, stable ones. To get a real sense of a machine's capability, researchers have developed more holistic benchmarks that capture multiple aspects of performance. These metrics help us track our journey from today's noisy, small-scale devices to the fault-tolerant machines of the future. It's like judging a car not just by its engine size handling braking reliability. One popular metric you might hear about is quantum volume. This number combines several key factors into a single score. It considers not only the number of qubits connectivity, how many other qubits each one can talk to, and most importantly, their error rates. To successfully run a quantum volume test, a computer must execute a complex, square-shaped circuit. The largest square circuit it can run reliably defines its quantum volume. Doubling the quantum volume each year has been a key goal for many hardware developers, providing a concrete, Moore's law-like target for the industry to chase. Another important concept is gate fidelity. A quantum algorithm is built from a sequence of operations called gates, which manipulate the qubits. Gate fidelity is a measure of how accurately a real-world quantum computer can perform these fundamental operations. A fidelity of 99.9% sounds great, but if your algorithm requires 1,000 gate operations, those small errors will accumulate and destroy your result. Pushing gate fidelities higher and higher toward 99.99% and beyond is a relentless and crucial battle. It's the difference between a musician hitting most of the notes and a virtuoso playing a flawless performance. Finally, we look at the ultimate goal, the creation of a logical qubit. We will have crossed a major threshold. It will signal the beginning of the era of fault-tolerant quantum computing. Section 9. A grounded vision. Promise, not hype. So, where does this leave us? We've journeyed through the strange and wonderful world of quantum computing, from the spinning coin of the qubit to the symphony of interference. We've seen its incredible potential to reshape science, medicine, technology. We've also faced the sober reality of the immense challenges that lie ahead. The key, as with any great scientific endeavor, is to hold both the promise and the reality in our minds at the same time. We should be inspired by the vision but grounded in the step-by-step nature of scientific progress. This isn't magic, it's physics, and physics takes work. The quantum revolution won't happen overnight. It won't be a single eureka moment but a gradual dawn. First, we will see small, specialized quantum processors outperforming classical computers on narrow academic problems. Then these devices will become useful for specific industrial applications in drug discovery materials. Science over time, as the hardware improves and our understanding of quantum algorithms deepens, their impact will broaden. Think of the early days of classical computing, the room-sized machines of the 1950s. Nobody then could have fully envisioned the smartphone in your pocket, but the fundamental principles were already in place. What does this mean for you in your daily life? For now, the best thing you can do is stay curious. Don't fall for the hype that claims quantum computers will solve all the world's problems tomorrow, but also don't dismiss the profound transformation that is slowly taking root. Pay attention to the breakthroughs in medicine and materials that may have their origins in a quantum simulation. Understand the importance of the global effort to upgrade our cybersecurity to be quantum safe. See this not as some distant, esoteric science fiction, but as a fundamental human endeavor to understand and harness the universe on its own terms.